Hello everyone, I'm sorry I'm slightly late, and well, there are not many of you, so let's wait a minute. Okay, it doesn't look like waiting a minute really helped, so I wonder what is happening, but do you have something before me? Is it English?
Yes, it was.
Yes, it is English.
So maybe it's one of the subgroups that is late or something. I don't know. Okay, let's start slowly. I will recap a small part of the lecture and then we'll go further. So there are two things we want to talk today about. One of them is the adjugate matrix. And another is the Cramer's rule. So, well, let's talk about both. So you might remember that the adjugate matrix is the following construction. So first of all, so it has several names. It has called adjugate matrix, or there is a second word, classical adjoint. This word classical looks strange, but it means that once upon a time it was named adjoint, and then someone named another thing adjoint. And now there are two different things named adjoint. So, well, here is a strange way how to, well, how to repair this situation, but we will use this word for this reason. It looks better. And inversion, just so you know, it is called союзная матрица or присоединенная матрица. Okay. So what is that? So the construction is as follows. Suppose we have matrix A. Then HA is the following matrix. We take the cofactors of the matrix A for each element of A. Okay, there are many elements. For each of them, we take the cofactor. I remind you that the cofactor is the minor of the corresponding element, that is the determinant that we obtain after crossing out one row and one column. So for each element, we cross out the corresponding row and column, compute the minor, then we put a plus or a minus depending on the place in the matrix in chessboard pattern. So this one is with plus and this one is with minus, etc. And the results are called cofactors. So those are cofactors. We form a matrix of them like this, and then for some reasons we transpose it. The result is called the adjugate matrix. Okay, any questions at this moment? So so what is the use of this wonderful matrix? Well, it so happens that it can be used to find the inverse matrix of A. A inverse is equal to 1 over the determinant times the adjugate matrix. So it is in some sense an ingredient that is like half-baked. We need this thing tells us the recipe how to get the inverse matrix from the original one. You first find the cofactors, then you arrange them together and transpose the result, and then you divide by the determinant. Just historically, it was so that this intermediate step of this process, it has its own name. Okay. We are not really going to use the adjugate matrix on its own. We are usually going to use it to find the inverse matrix by this formula. Any questions? Yeah, so please, yeah, we didn't have online lessons with you yet. So this, unfortunately, we will have a lot of. So please, if at some point there are any questions, don't hesitate to interrupt, okay? Because in real life, it's easy to see you, and here you can write into chat or you can like raise hands in Zoom, but all of this is inconvenient. It is better to simply interrupt and say whatever you wish. I won't mind, okay? Okay. So once again, so this is the formula for the inverse matrix. This is the adjugate matrix. So it may be used to find the inverse matrix. However, is it easy to do so or not? Let's find out by, well, doing this on an example. So suppose I have the following matrix.
I'm sorry, but could you please send us the link of this?
Yeah, sure. I can resend it. I already did this, but in the beginning, so not everyone sees. Let me recopy it. So you can, again, it is more easy usually to look through the demonstration because you see where, at which exact point I am. But if you prefer using the link, it is up to you. And I will try to not forget to post them on Wiki regularly. So they will be open after the seminar too.
Thank you.
Okay, so very good. So here is a matrix. I wish to find its inverse using this new method. Okay. So to do this, I have to find a special minor for each element. So for this element, I take this minor. Okay, I cross out the first row and first column. The result is 3, 4, minus 2, minus 3, like this. For the next element here, as I have transposed here, I should compute not the minor of this element, but of this element. Okay, so it is 5, 7, minus 2, minus 3. Moreover, as it is cofactor, not minor, I need to put a minus here because this cell has the sign minus associated with it. Any questions for this particular element? Okay. Is everything fine? 3, 2, 1, no questions. Okay.
Wait a minute. In
Don't.
what case we have to write that element? For example, when we were finding determinant, we were multiplicating it on our minor, yes? And
not multiplicating,
here,
multiplying. Okay. English language is hard. Okay. Yeah.
So in this case, we don't need to multiply by the element. I mean,
yes.
In the first case, like 2, yes?
Yes, we don't. But when if you look in the lecture notes at the proof why this thing is related to the inverse matrix, you will see that if you multiply this matrix by the matrix A, then the elements from A get multiplied by minors from the adjugate. And together you get something like the formula of the determinant.
Okay, thanks.
So now here we have only the minors themselves. Okay, very good. So now the next one, so I consider the last element of this column. So while I go here through the row, I go here through the column because of transposition. So for this element, this is the minor. So let me write it down, 5, 7, 3, 4. Now here I have minus something, that is this. Here I have plus something for the central element. So I cross out the center. And what I obtain is from the corners. Here I have minus something. And so I for this element, okay, right? I need this cell. So I take the opposite element, this one. It is 2, 6, 7, 4, like this. Now this one is for this element. So it is the bottom left corner. This one is with minus, and it is for this one. So it is 2, 5, 5, minus 2. And the last one is for this element. So it is this corner. Once again, please think if you whether you understand everything, how I got it, because it is important. Okay, now what remains is the simple method of computation. So let's quickly compute those 9 determinants. This one is -9 plus 8. This one is 15 with plus because minus and another minus. And this one has 1 minus, second minus, and the third minus because of this. So it is minus 14. 20 minus 21. 18, again, 1 minus and the second one. Plus 20 plus, because here we have a minus and this goes with a minus. Minus 6 minus 35. Minus 8 plus 42. Minus 12 minus 15. Plus 4 and plus 25. 6 minus 30. I can simply now enter the subtract correspondingly. Let me quickly finish. So if I have no mistakes, then this matrix is the adjugate matrix for the matrix A. Now to find the inverse by this formula, A inverse equals 1 over the determinant. By this, I need to find the determinant. Well, we've learned how to find determinants for 2 seminars. So basically, we could use the definition or equivalently the Sarrus rule. We could use Gaussian elimination, but it makes more sense to use Laplace expansion, to expand by some row. Indeed, for example, if to find the determinant of A, I expand by the first row like this, then I can use the fact that those numbers were already computed in this matrix. I don't need to do this work twice. So I obtain the following: 2 times minus 1 from this cell, then this determinant. So I go through the first row, but this matrix is transposed, so it is the first column. Next one is plus 5 times 38 and plus 7 times minus 27. Does everyone understand why there is a plus here?
Because the determinant of the second multiplication will be negative one, will have a sign negative. And then we this minus is multiplied by the minus and we get a plus, yes?
Yes, but that's, well, technically, yes, but that's not what I meant. I mean rather, well, okay, that's not only technically correct, that's for sure correct. What I meant is that this formula has a minus here because that is the formula through minors, formula of expansion of a determinant through minors. But there is a second way to write, but this minus can be put into this part, and then it is called cofactors. Like, a second to copy the formula. Like in the lecture, it looked like this. So there are 2 ways, right? You can put the minus over here, or you can put it inside this expression. I remind you that cofactors are simply those determinants, those minors, multiplied by plus minus 1 from this. So when I computed this 38, the minus is already inside. Okay. So are there any questions about finding the determinant? I skip the computation for a moment because I'm going to do it more intelligently in a moment, but for this part. No questions? Then let me say that multiplying by 38 and 27 is too hard for me. There is a better idea. If you look at this matrix, it is much easier to multiply by those numbers, -1, 1, and -1. So let's expand by something that corresponds to them, that is, by the first column of the original matrix. If I expand by the first column, then I get those determinants. So I obtain the following: 2 times -1 plus 6 times 1 plus 5 times -1. That is -2 plus 6 minus 5, which is -1. Much easier. Obviously, that's, well, like a coincidence where that's very happy that in this particular matrix, I mean, very lucky that in this particular matrix, one row is very easy to use, but still very convenient. So what remains is to compute the inverse matrix. I simply reverse all the signs. And that's it. Questions? Okay, no questions. Then that is all about the adjugate matrix. So once again, the adjugate matrix is a tool that we can use to find the inverse matrix. However, please note that usually it is easier to simply use the method we already know. I remind you that there was a method like this. We append the identity matrix to the right-hand side from the matrix A and do several steps until you can read the inverse matrix from the right-hand side. So usually in practice, this method is easier than this one. This method is mainly useful for 2x2 matrices. For 2x2 matrices, it is extremely easy because all the minors will become 1 by 1. That is the element itself. There are no computations then. So it is very useful for 2x2 matrices. And it also has some theoretical uses. Later, we will use it in some formulas. So the fact that we have a formula for the inverse matrix is kind of useful. This thing is like not a formula, but an algorithm, a process, how to find. And this is like a result already given by a formula. So in some sense, it is better. No more questions right now? Then let me move to the second topic of today's discussion, the one that has like more problems. And that is the Cramer's rule. So what is it about? I remind you that once upon a time, we considered the following system of two equations with two variables. When we were first discussing determinants, I wanted to motivate you, and I said that there are formulas, explicit formulas that give the result. Explicit means явные формулы. So they, well, we could write them like AD minus BC or something, but now that we know determinants, I'm sorry, we're able to make mistakes. Now that we know determinants, the formulas look like this. And this one is I'm going to write the general formulas in several moments, but still, for 2x2 case, the formulas are like this, and they look similarly for larger cases. So, well, so that's why we're interested in obtaining the same formulas for n by n systems. So this determinant in the nominator, we usually denote it with delta capital. This letter is delta capital. It is an ancestor of Russian letter D, заглавная. And this is usually denoted as delta x and delta y corresponding. So the general rule is as follows. If we have, let me in fact use the next slide. If we have a system with n variables x1, etc., xn, and n equations. So unfortunately, Cramer's rule doesn't work at all if the system is not n by n. If the number of variables doesn't equal the number of equations, Cramer's rule is useless. We can't use it. But if those numbers agree, if they're equal, then we can find the following determinants. Delta is the main determinant of the system. It is simply the determinant of the matrix of the left-hand side. Okay, I take all those coefficients together in a matrix and find the determinant. That's it. Now, delta 1 is the determinant where the first column gets replaced by the right-hand side, and all the other columns stay the same as they were. Etc. So each delta I is as follows. We take I'm sorry. We take the ith column. Okay, so all the other columns stay the same, but we take the ith column and replace it. So everything else is the same, but instead of the ith column, which should be between I minus first and I plus first, instead of it, we have B1, etc., Bn. We throw away one column and instead of it, put the right hand side. So the theorem about Cramer's rule claims that x1 equals delta 1 divided by delta, x2 equals delta 2 divided by delta, etc. xn equals delta n divided by delta if delta is non-zero. So this is a second limitation of Cramer's rule. If delta equals 0, you obviously can't use those formulas. That's life. Still, we will discuss this situation some minutes later. We'll return to the question what happens when delta equals 0. But right now, so this formula is useful only when delta is not 0. But when it is not, it gives the formulas to find the answer. And it shows that the answer exists and is unique. If delta is non-zero, you find some particular numbers by using those formulas. So this system has one solution and it is given by the formula. Any questions if there are no questions at the moment, let me then write down a system of linear equations. Unfortunately, there are some problems with copying it, so let me simply rewrite. Like this. So here is a system of 3 equations with 3 variables. So the prerequisites are fine. We can use the Cramer's rule. So we have to find 4 determinants: delta, delta 1, delta 2, and delta 3. So let's start with delta because it is important whether it is 0 or not. If it is 0, we may stop at this point. The rule won't work. So I have to find this determinant. I'm sorry, it slightly lags. Okay. So how to find it? Well, there are many ways. For example, I can subtract this column from those columns with some coefficients because 1 to 2 are quite easy to deal with. And also I see that 7 minus 6 is nice, etc. Well, kind of my intuition tells me to do this step, but again, there are many other possible steps to do, like many of them. You can kind of abuse the fact that 2 plus 3 is 5 to make this 0, or 2 plus 1 is 3 to make this 0, etc., etc. Many possible variants. Still, suppose I subtract the first column twice from this and from this. Then here I get minus 1, 1, 0, 1, minus a 2, 0. And now I may expand by this row. So the result is a smaller determinant, right? It is 1 times the smaller determinant plus zeros, which I can ignore. And this is 2 minus 1, that's 1.
Could you again explain this method with expanding of column?
Okay, so once again, when I expand the determinant, there is a formula that says that the result is as follows. For each element in this row, I consider this element that is 1, 0, 0. I consider this sign that is plus, minus, plus. To obtain the signs, I need to color my matrix in a chessboard pattern like this, okay? Like this. So for this third row, I get plus, minus, plus. And for each element, I consider its minor. That is, the matrix I obtain after crossing out the corresponding row and column. And this entire expression equals the determinant. That's the formula.
Okay, thanks. So the main goal of this method is just to make bottom row
Any row
with zeros.
Yes, so if we make enough zeros in any row or any column, I can after that expand by this row. And when 0 gets multiplied by something, there is no need to compute this something. I don't need to know the value of this to find this product. It is 0. So this way, I kind of make my determinant smaller. I only need to consider now this part.
Okay, thanks a lot.
So I obtain, in this particular situation, I obtain 1. Now I have, unfortunately, 3 more determinants to compute. So delta 1, I replace the first column by the right-hand side. So the second and third columns remain the same, okay? I repeat them. And the first column I replace by 10, 3, 3. Now I have to find this determinant. Again, there are many things I could do. But for example, let me subtract like this. Then let me subtract like this. Oleg, yes, very good. I'm sorry, it's not very convenient to read the chat. So please try to not write too much to it. It's very inconvenient for me when I'm drawing.
Okay, so sorry.
And not a huge problem, but just in the future. Please try to avoid it. So this way I can, I did this because I see that 2 minus 5 is divisible by 3. Now I can put 3 outside of this row. I'm trying to solve different parts by different tricks so that you can, again, have a chance to refresh what kind of operations we can do, etc., etc. So now, when I see 1 and minus 1, I can now use columns, not rows. I can do operations with rows and columns, so I have some freedom to choose. So what happens now is this. And again, I expand by this row. It's a coincidence that it is the same row as last time. It could have been something different. And so 3 remains, obviously. And this is 1, and it is with plus. And what remains is this smaller determinant, which is easy to compute. It is 26 minus 25. So the result is 3. And we can use it now to find x1 by Cramer's formulas. x1 equals delta 1 divided by delta, which is 3 divided by 1. Are there any questions at this moment?
Have we subtracted the first row from the no, I mean, have we from the second row, not row, but column subtracted the first one?
We added so that 1 plus minus 1 is 0.
But I'm not that sure how we get it from the previous version.
Here,
with the 1 and
this
minus
one.
1. We multiplied by, we just by 3. Multiplying it.
We divided this row by 3, multiplying the determinant by 3 back. So the result is equal. This is called like taking a factor outside from the row. Вынос множителя.
Yeah, I just didn't notice.
Don't worry.
Thank you.
Again, yeah, I could write all those L something, 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 D something, something, but it is, well, kind of not extremely convenient, but sometimes helpful to understand what is happening. Okay, delta 2. So here, the first column is the same as in the original 2, 3, 1. The second column is the right-hand side, that is 10, 3, 3. And the third column is the original, that is 4, 2. Okay, like this. So once again, I have to compute it. I did something interesting with the other group with this determinant, but I forgot what. So I think we subtracted this from here.
Well, maybe actually we can change the rows by the place, like the third one to place in the place of the first one, and the first
Okay,
one
we
to place.
could. And what's the goal? Why would we need it?
Just I think it will be more convenient to subtract. Maybe.
Well, if we are not trying to obtain reduced row echelon form, but we were just juggling things, then it doesn't really matter where exactly is the best row. So let me subtract the third row from the second. Then I can divide by 2 and I obtain a very easy row. I like rows that have small numbers and that have some zeros inside because it is easier to subtract them from other rows. I could do the same with the third row immediately, subtract it 3 times from here and 2 times from here to obtain 0 and 0. But instead, I used some clever trick to make computations easier. And now the result is as follows. Here I have 0, 3, 1. And here I have 0, 10, and 5 minus 2, that's 3. And now I may expand by the first column. It has 0, 1, 0. So the result is minus this. This minus is because this element stands at a place that has minus in chessboard coloring. Okay? Okay, the only problem is that the result is not correct. That's because I forgot this 2. I have 2 times the determinant, so I have to carry it with me. Then the result is not -1, but -2. So x2 equals delta 2 divided by delta, that is -2 divided by 1, that is -2. I can similarly find delta 3, let me skip it. As far as I remember, it equals 2. At least that's what my notes say, and that's what Alex says, so maybe everything is fine. Okay. So we have completed the exercise. It took only 3 slides, and we finally found the solution of this original system. x1 equals 3, x2 equals -2, x3 equals 2. Questions?
Could you again explain when the part where we are making determinants delta 1, delta 2?
How do we make them?
What is the logic of them?
Yeah, okay. So again, I take the same determinant. So I take the left-hand side. And then to find delta 1, I throw away the first column. This column 2, 3, 1, it is not present here. And instead of it, I put the right-hand side. I put those numbers in the place of those numbers, the ones that are with x1.
Okay, so if it would be a matrix 4 by 4, yes, we have to put a column with answers, the last column, into places where we have to find the x1, x2, x3, x4.
Yes.
Okay, thanks.
So yes, for each variable, there is a corresponding column. And so for each variable, we have this delta I So here we have it for the first column, here we have it for the second column, and similarly I can find it for the third column, but I skipped this part because it will take too much time. So you can see that this process solves a system, but it takes time. In practice, it is much easier to solve this system using Gaussian elimination. The reason for this is kind of that Gaussian elimination will do some work on the entire matrix simultaneously. And here we have to simplify this determinant separately, this determinant separately, this determinant separately, and the fourth one separately. So unfortunately, this method is not very useful. It takes too much time. However, there are situations when it is useful. There are three such situations. The first one is, well, again, in theory, sometimes it might be helpful to put into some formulas the solution of some, well, system of equation. We will see such examples later when we study geometry in our course. Still, the second idea is that if the system is 2 by 2 with two variables, like in school, then those determinants are very easy to compute and those formulas work quite well. Obviously, it's not very hard to solve systems 2 by 2 by any method, but still, this method looks quite good in that situation. And the third, most interesting reason is when you have a system with parameters. If you have a system with a parameter or several, then Gaussian elimination becomes very nasty because you have to consider cases when parameter equals something, doesn't equal something. That's always not nice. This method will help. We will see it in a few moments. Before that, we need first to solve a special auxiliary problem, a well, you will see in a moment. But still, we are going to solve a small exercise right now, and after that, we are going to solve some systems with parameters. So first goes an exercise. Well, please consider the following system. Very easy one, 2 by 2. So delta is 36 minus 36, that's 0. So as I said, Cramer's rule doesn't work here. Still, let me compute delta x and delta y. Yeah, for small systems, we sometimes call the variables not x1, x2, etc., but xy or xyz, right? That's simply tradition. So if they are called x and y, then I call these determinants not delta 1 and delta 2, but delta x and delta y. Again, tradition. It doesn't really matter. So it's easy to compute that they also equal 0. So unfortunately, in this case, the Cramer's rule doesn't say any information about the solutions. What it does say is that there are either no solutions or infinitely many solutions. However, it doesn't say which case is the correct one. If there was one solution for the system, this method would find it. So you might remember, I hope you remember, there are 3 possibilities for each system. It can have no solutions, 1 solution, or infinitely many solutions. So the situation with 1 solution is covered by the Cramer's rule. If Cramer's rule doesn't work, only 2 situations remain, but which one we can't see. So, okay, this is a very pessimistic example. It shows that, well, we didn't really learn anything. Now we shall abandon Cramer's rule and solve this system by usual methods. So why I am showing you this?
I suppose it's no, but I think that's not that bad even to know that there's maybe there's one situation, one case, which is the system may have a one solution. We remove it, and so we can now check if it has any solution. If you can find one solution, then there will be infinitely many.
That's correct, and in fact there are some fields that use this logic, but in fact what I wanted to talk about is a small modification now of this system. Please look at another system I have created for you. Here this determinant is still 0, but delta x is now 18 minus 30, which is minus 12. And delta y is something else, 8. It doesn't really matter which particular numbers. So here we also can't use Cramer's rule. You can't divide by 0, but there is a theorem that says that in this case, we can immediately find out that there are no solutions. To be more precise, the theorem goes as follows. If delta equals 0 and sum of the delta i's doesn't equal 0, if there is at least one such I, then the system has no solution. The idea of the proof, I won't give the proof, but the idea is as follows. You take the proof of the Cramer's rule, which is, as far as I understand, on the next lecture. The lecture didn't have time to finish it on this one. So you take the proof and at some point, you will obtain the following formula. Delta multiplied by xi equals delta I. And in the proof of Cramer's rule, the next step is that you divide by delta. That's how we obtain those famous Cramer's formulas. You first obtain those formulas and then you divide by delta. But if we are in the situation of this theorem, then 0 times xi equals some non-zero number. That is impossible. So we can immediately conclude there are no solutions for our system. And the part that is over here, it will work whether delta is 0 or not. This part of the proof won't depend on delta. The only place where we use that delta is non-zero is when we divide by delta. Again, we will fill the gaps after the lecture. You will see in the lecture how to fill this part. Questions? So if the Cramer's formulas say that something non-zero is divided by something 0, then immediately there are no solutions. And if all of them are 0 divided by 0, then unfortunately it is like no information. We don't know. Okay. That being said, Let me consider now some systems with parameters. This wonderful system has two parameters, and moreover, they are also with some trigonometric formulas. That doesn't look nice. I should have made larger white spaces here. It's not alpha x, it is cosine of alpha multiplied by x, okay? Otherwise, it would be too hard to solve. So this system, we can solve it by using Gaussian elimination, but that would require considering many small cases, like does cosine of alpha equal 0 or not? That's not very nice, because cosine alpha equals 0 means that alpha itself has many possible variants, and so on and so on. So instead, let us use the Cramer's rule. The main determinant of the system looks as follows. It is cosine squared plus sine squared, which is 1. So it is non-zero for any alpha and beta. No matter what are the values of the parameters, alpha and beta, delta is still not 0. Interesting. So what remains is to, well, find delta x and delta y. So what is this formula equal to?
This is the cosine of the sum to angles. So cosine alpha
You are
plus
right.
beta.
You are right, but I made a mistake. It should be plus here, because here is a minus and here is a minus. I'm sorry,
yes.
I didn't do it intentionally. And so with a plus, what is it
Then
equal
will
to?
be then the subtraction of the alpha and beta.
Alpha minus beta or beta minus alpha?
Alpha minus beta.
Or beta minus alpha?
Alpha minus beta. No, but
Any more opinions?
It's the trick.
There is some trick, right? So what is the trick?
Alpha minus beta.
I also prefer the first variant.
Okay,
alpha
maybe
minus
we
beta.
need to have a vote. Alec?
Alpha minus beta. Yeah.
Aha, so many votes. Well, okay. In fact, that is the same. Cosine is an even function. Cosine of plus something equals cosine of minus something. Okay, now let me do the same, but for delta y, I obtain the following formula. So what is its result?
Cosine alpha plus beta.
No. It's not a cosine.
Alpha plus beta.
Sine
Yes.
of alpha.
Well, sorry, just alpha plus beta? You think that the result is an angle?
No. I meant that maybe sine or cosine, something like that.
Sine or cosine? I'm sorry, but you have to be more exact.
This is a sine, and this will be a sine alpha minus beta.
It's sine beta minus alpha.
In fact, beta minus alpha. Here for the sign, it matters, and it is beta minus alpha because beta here is
I
in
see.
the sign. And so, well,
Yes.
altogether, we obtain the result that x equals this divided by 1, that is simply this cosine, and y equals, well, the sine of the same angle. Okay. Now we have practiced with one problem. Now let me have another one. I forgot. This problem can't be copied for some stupid reasons, so let me rewrite it by hand. Right. So here is another problem where we also have a parameter a here and here. And this parameter, well, kind of makes things again not very nice for using Gaussian elimination. So instead, let's use Cramer's rule. This is a squared minus 36, which is, as far as I know, a minus 6 by a plus 6. So unfortunately, this can be 0. That's life. Still, let's not become disappointed too early. And let's compute delta x and delta y. So for delta x, I replace the first column by 2, 3 by the right-hand side. And the second column remains 4a. So this is 2a minus 12. Or it is easier for me to write it as 2 times a minus 6. Because this way I see when it equals 0 and when it doesn't equal 0. Likewise, delta y is a923, 3a minus 18, that is 3 times a minus 6. Well, this is like an artificial example, so like numbers coincide, etc. So now there are 3 possible cases. A can equal 6, a can equal minus 6, or it could not equal either of them. In the last case, we immediately obtain that x equals delta x divided by delta, that is 3 divided by a plus 6. A minus 6 cancels. And y equals 2 divided by a plus 6. Okay, is this case understandable?
Yes.
Please note, yeah, question? No.
But in X, there must be 2, not?
Oh, sorry, I switched them for some reason. This one is 2 and this one is 3, thank you. I don't know why, no idea. So, thank you. So this, please note that getting this was much easier than using Gaussian elimination. We did it very fast and easy.
Do I understand correctly that if we have a is equal 6 or a equal minus 6, then we will get that the our system of equations does not have solutions.
Not really, no. But in this case, with
Well,
minus 6.
with minus 6, yes, but with a is equal to the 6, then we have all equal to 0, and then we have two possibilities. That is, there are no solutions or there are infinitely many solutions.
Yes, now it's better. Yes, so the situation goes as follows. I'm sorry, I have some problems. Okay. Do you also see this warning, right?
Right.
Yeah.
Yes, even during the recording.
Okay. Yeah, it's part. This warning is not part of Zoom, but part of the whiteboard. Okay. The recording. So you have the recordings of some previous seminars?
Yes.
We got the recording. We have the playlist on the YouTube channel, and
I don't
also,
have it. Can you give it to me then?
okay.
Yeah, I can.
Please, someone send me into Telegram at some point. Thank you very much, because I don't have it.
Okay, I will send you after lesson.
Yeah,
After
sure.
like
Yeah, sure. Doesn't matter when, but okay. So let's return. So this case. So the situation is that what I was talking about, that delta equals 0, delta x doesn't, that by using the theorem that I stated, this automatically means there are no solutions. And indeed, there are no solutions in this case. And for this case, unfortunately, Cramer's rule doesn't work at all. It can't give us any relevant information, so we have to fall back. We have to consider the system. We have to put this 6 instead of A and solve this system by hand. Well, those equations are proportional. In fact, you can use one of them to make the other one 0. So I can even not write any matrices because the system is very easy. So the solution, so there are infinitely many solutions. You can write them like this, or the other way of writing down the same answer is like this. So the fact that Cramer's rule doesn't work doesn't mean we can't solve the system, right? We always have Gaussian elimination. And again, it was kind of easier. All the procedure we've done is easier than if we were doing Gaussian elimination with parameters, because it would be really messy. We would have then cases A equals 0, A equals plus minus 6, A equals something, many cases. And this way, it was pretty easy. I heavily recommend this method. Any questions?
No questions.
Okay, if there are no questions at the moment, let me have a final problem for today. It's not really a problem, it is a discussion. So let me remind you one problem from a home task that was some time ago. I don't remember which one, but there was a problem that looked as follows. Find f of x like this. Find such a polynomial ax squared plus bx plus c such that f of minus 2 equals 19, f of 1 equals 4, and f of 2 equals 7. Maybe it had some different numbers. I'm not sure. It doesn't really matter. So we're not going to solve it right now, but let's remember how it was solved. We said that if we put this minus 2 into this formula, you get that a times minus 2 squared plus b times minus 2 plus c equals 19 from this fact.
Then we said that if we put a 1
Mhm.
in the formula, then we will get the result 4. And
Mhm.
then we and then the same thing for the third
Mhm.
x, and in that way we get the system of linear
Mhm.
system of equations.
Thank
We
you.
can
Yes.
solve, and
Yes, we can solve this system, but we won't. Now, let me go in a different direction. So this system, we can solve it by Gaussian elimination, but suppose I want to solve it by Cramer's rule. I won't do it because that's not very useful, but let's start. Let's compute the main determinant delta. I claim delta will be useful. Well, how to find this determinant?
well, maybe we can the second row subtract from the third one.
We could.
Uh,
However,
that won't work well.
no, that will work fine. This determinant is easy, but that's not what I mean. You can do many kinds of like operations on this determinant, but I want you today to look at it and immediately say what it is equal to. Is it possible?
Is it equal to 0? I'm not sure. Just because there's some matrices which by side you can say that it's equal to 0, but I don't think this is the case.
Yeah, but that's not the case. It is a more interesting case. Anyone remembers it? We already had it. It was just disguised. It looked differently. Someone is writing in chat.
Somebody supposes the -1 equal.
I mean, I don't know the correct answer as a number. I know it is some operation how to do, but I think no.
Can we
No,
just
not -1.
calculate it by the last column?
We can, but again, there is an easier way. Well, not really easier, but there is some ready answer that we already know. We can use it.
Will that be -2 or 2?
Guys, you are no. There is no reason to guess. The answer is not so easy. But there is a
No, I just think that if we have, I thought we have already answer inside of the matrix. This is a determinant, I know. I just mean that.
yeah. No, the question is what kind of a determinant that we already know is this one. And maybe let me transpose it.
Skew symmetric one.
It's not skew symmetric,
No,
for example, this and
no.
this. Let me transpose it, so maybe it will refresh your memory. Maybe this one is easier. Anyone?
Oh, it's with ones, yes. So we can bring it to form with zeros, maybe.
No, that's not the case.
No, yeah, no, we can do some operations, but I don't want to. I want us to remember that we already know the answer.
Let us a couple of minutes to think.
Yeah, we have 7 minutes, so, and that's the last exercise.
It is the sum of the diagonal, but no.
The answer is 0.
No,
Oh, okay.
don't try to guess the answer. That's not very easy to do. Try to remember what kind of a determinant is this. It is a very special one that I asked you to memorize, and evidently no one did so. But that's fine. This happens every year.
Oh, this is no, there's a special name to such matrix even.
Okay, you don't remember the name, but you remember that something like this happened last time. So what kind of a matrix is it? How does it look like in the general case?
Well, it's that should be yes with the ones, and there's also some other elements with the instead of -2 and 2.
Okay. And then what goes in the next rows?
And the next rows goes.
Okay.
Can we suppose that the first row is like the second, but in the power of 0?
Yes, it is. So there are some elements that are in some powers in each row. You should remember the following matrix. From the last time. This is called Vandermonde matrix.
Yes, Vandermonde. But
And this is a particular example where x1 equals -2, x2 equals 1, x3 equals 2. This is just one particular example of this general construction. So do you remember the answer? When I produced this formula, I said that we don't need to remember the process, but we need the resulting formula. It will be useful. Well, today is the day when it is useful.
well, it will. That will be actually x-2, x2 minus x1 as the first bracket, multiplied by the x3 minus x1, and so on.
There is a compact way of writing this down.
Yes.
Product of all possible pairs like this. So here I have this minus, and then this becomes the following: 1 minus -2, 2 minus -2, and 2 minus 1. This is x2 minus x1. This is x3 minus x1. This is x3 minus x2. And that's it. So on one hand, we can now compute the particular result. It is like 3 times 4, 12, minus 12 or something. But that's not very important. What is important is that it is non-zero. So this, yes? No. This allows me to state a wonderful general theorem. Suppose let x1, xn, no, x0, xn is more nice, be different numbers. y0, etc., yn, any values.
But can we just, no, we just calculated only delta, but maybe we should
Yeah,
also delta x, delta y.
Unfortunately, this will be not very nice. They will be not, they themselves will not be Vandermonde matrices because the right-hand side is arbitrary, is anything.
No, I
So
just think that because we got a Vandermonde matrix, then we should got this type of system of equations should have some particular one situation, like it has only one solution, or
that's exactly what I'm talking about. Yes, so I just want now to not finish anything about this particular task, but state a more general theorem that if I have any kind of points and any kind of results in those points, any values.
I thought that by induction we could get, from looking at the one case, we could understand what may be the general one. So
Yeah, there is no need to do any induction here. Simply, if we consider a unique polynomial, if we consider some function such that f of x0 is y0, f of x1 is y1, etc., then there is a unique such polynomial with degree n or less. That is, f is an times xn plus an minus 1 times x to the power x minus 1, etc., etc. The proof is as follows. Delta, we can similarly construct a system, and delta equals, so x0 to n minus first power, x0 to n minus second power. No, to n. x0 to nth power, x0 to n minus first power, etc. x0 and 1, well, x0 to the zeroth power, x1 to this power, until xn. This is, so to make this into Vandermonde determinant, you might need to transpose it and to exchange some rows, etc. So the result is plus minus the corresponding determinant. I'm not sure which one, but it doesn't matter. And then you get, well, the product of all possible pairs. And this is non-zero. If those points x0, x1, x2, etc. are different numbers, then those differences are different numbers. So this is non-zero. We multiply many non-zero numbers, we get something non-zero automatically. Thus, a solution exists and is unique. Unfortunately, this theorem doesn't tell us how to find it, because using Cramer's rule to find it is kind of silly. It will take too much time and steps. Instead, we usually use simple Gaussian elimination, or there are some other tricks we will learn one day later. But still, it's nice to know that this problem is always solvable. That's it. That's what I wanted to talk about, to show you some kind of use for Cramer's rule and use for Vandermonde determinants simultaneously. I think we are more or less done for today. We've done many exercises. If there are any questions, please ask.
But how can we use actually this theorem just in practice for?
You can't use it practically, but it gives you like a direction. When you know that this kind of problem is solvable, then you know that, well, that it makes sense, to, like, how to say, to try to do it, right?
So we just can check if it has this system of equations a solution.
Again, we know that such a function can be determined by its values in n+1 point. We know that if someone gives you n+1 points and the values of the function, you can find out what was the function if it is a polynomial of small degree. For example, any quadratic function, any parabola, can be given by 3 points. And any 3 points give you a parabola or a straight line.
Yeah, I get it. I just was thinking, how is it connected to the task? No, to the next task, but example.
Yeah, it was meant as the start of thinking. We started with a particular example, and so we got a big theorem. But again, yes, unfortunately, it doesn't tell us how to find. To find particular solution, unfortunately, yes, it doesn't help.
So it has a theoretical value.
Yes.
Sorry for interrupting. It was accidental.
No, that's exactly what I tried to say. Yes.
Yeah. Okay. Thank you.
Any more questions? Okay, maybe let's then stop at this moment. We are far, in fact, late. I'm sorry. And we shall meet like next time. Yeah. About the next time, I don't know whether we have something on the next week or not. It depends on whether we have a lecture or not. I will write you later.
I have a question about the recordings. Do you have a folder or something with recordings of seminars?
Again, I don't have anything because the study office has them, but someone of you told me
owns them. I will ask him to send.
Yeah, in the chat there is a link.
I've already sent it the link with playlist on YouTube.
Yeah, and there's also one in the Zoom. It was sent. The link to the playlist where is all videos of seminars.
Okay, and
It's,
also Commission had sent us the recordings from the Zoom with special concepts, something like that. So we have to learn how to watch the recordings.
Okay, whatever. 2 ways is better than 1.
Okay, so bye. Thanks a lot for seminar.
Good luck. See you in a week or in 2. I don't know.
Thank you.
Thank you very much.
Yeah, thank you for the seminar. Goodbye.
Thank you very much. Goodbye.